Wavepacket dynamics using the Crank-Nicolson and Split-Step Fourier methods. So, in the abstract, basically, I have just explained that we have used two numerical methods, which is basically Crank-Nicolson and the Split-Step Fourier, for solving of one-dimensional time-dependent and Schrödinger equation, basically. Okay. So these methods basically apply to simulate the dynamics of quantum wavepacket in the various potentials, including free space barrier, harmonic oscillator, and double well potentials. So these numerical solutions basically implemented in MATLAB to get the accuracy, efficiency, and conversion of probability and its energy. So basically, Schrödinger introduced the concept of wave mechanics and proposed the time-dependent Schrödinger equation. Okay, that's why Schrödinger was a scientist who proposed the time-dependent equation, and later on, which called it Schrödinger equation. Okay, so just a second. Okay. So later on, we also called it that study is developed the Crank-Nicolson method is found to be more accurate but computationally expensive, while the Split-Step Fourier method is faster but less accurate for the certain potentials. So in the study of highlights the importance of choosing that appropriate numerical methods for simulating of quantum system that provides a useful reference for future research as well. Okay, so here is the abstract I have just written and the introduction, how we have used the Schrödinger equation for the fundamental quantum mechanics that describes the evolution of quantum system over the time. So here is the Crank-Nicolson method for the time-dependent Schrödinger equation. So these are the equations used. We call it Schrödinger equation. Okay, Schrödinger equation. So in this basically finite method is the second order accurate in time and space, which is basically unconditionally stable and conserves probability and energy. So here is the table, which is basically the comparison of Crank-Nicolson and Split-Step Fourier methods, which provide us its key features and its advantages as well. Like the Crank-Nicolson is basically stable, accurate for long time evaluation, and the Split-Step Fourier is SSF, basically fast and efficient for large grids. So introduction of the time-dependent Schrödinger equation. The Schrödinger is the basically equation which normally evaluation of the quantum system over the time, and this equation basically is a partial differential equation which we need to solve analytically except for simple systems. So the numerical methods are necessary for complex system. So that equation is used in various quantum phenomena, especially in the quantum mechanics, compared with the different propagation schemes for the time-dependent Schrödinger equation, including the Crank-Nicolson and Split-Step Fourier transform. Okay, so here is the importance of numerical methods. Yes, I have just added, like we need to use the simulate the quantum systems. These quantum systems are numerical methods for time-dependent Schrödinger equations. And the next one is the numerical methods overview, and we have just explained everything in it. Description of Crank-Nicolson method, description also added, and you just read it and you will understand like how the method is smooth and potential smooth potentials. Okay, accurate for the smooth potentials. And description of split step Fourier method, which is basically how that method is implemented over the exponential split operator method to solve the Schrödinger equation for above threshold ionization. So the purpose of study here is the purpose of study for the Schrödinger equations, how we use, and I have just explained previously, and the potentials considered basically also added, and the numerical solutions for the how we have implemented in the MATLAB code. Okay, aim of study also added with the significance of study, problem statement, mathematical approach as well. These are the equations used in our system, like Schrödinger equation. These are the Schrödinger equations with the strange splitting approximations, and the methodology also here, and the parameters used in our model for the MATLAB terms, and design MATLAB simulation with its analysis. Yes, these are the output results according to the time evaluation of the wave function basically. Okay, potential and initial wave functions, and next part is the evaluation of Crank-Nicolson probability density evaluation, and color bar basically represents the magnitude of its. Next part is basically split-step Fourier probability density evaluation. Wavepacket using the split-step Fourier transform, heat map, as well as its energy comparison graph, its time evaluation, its time evaluation with different time scale, Wavepacket using the Crank-Nicolson method. These are the results and discussion basically, and overall results demonstrate the effectiveness of Crank-Nicolson and split-step Fourier methods for solving the time-dependent Schrödinger equations. Here is a conclusion and references also added in it. So let me just provide you a demo how you can run that model. This one. So here is the MATLAB code. You just need to run the function and you will get the output results accordingly. Okay, here is a probability density, real-time simulation results, animation of real and imaginary values of Schrödinger equations with the time evaluation. Here is the time evaluation according to the different time probability as well. So basically, with the varying of time, it also the data is providing us the different time scale with the different output results accordingly. Let's see the output results of time evaluation according to different time scales. Okay, so these are the output results accordingly. You just check it, and if you need to ask anything, you just ask me. I will answer your questions. Thank you.